Okay, hello everyone. So let's continue our topics about multi-component distillation. And after we know how to calculate the stage of distillation in equilibrium stage for shortcut method, the Fenske, Underwood, and Gilliland, now let's have a look how to sharpen the calculation using exact method or rigorous method. So let's have a look. Okay, so in this one here, let's just review a little bit about the how to calculate the distillation stages. So in the shortcut method, we calculate the NM using the Fenske method, and then we calculate the RM as well using the Underwood method, and then we can get the reflux ratio based on the specification that we have from the problem, and then we can get the N or the number of equilibrium stages using a graph in the Gilliland correlation. So that one we can get all the data from the rigorous method. So now we want to have more rigorous method or the exact method where we want to predict the equilibrium, the equilibrium stages, how many stages that we need in the exact one. The first one for the exact method, it will require data from the shortcut method, which is the N, the reflux, and also the N and so on. And then it can be used to calculate the equilibrium stages with more accurate and can be used to calculate the concentration and temperature of profiles in every tray. If you remember, in binary distillation, you can get the temperature and concentration in each stages. So we won't have to get that as well. And then also it is a tray-to-tray calculation. So it is iterative until you get the specific the specific value. And also we use the assumption of the constant model of flow. In the beginning, you should have the multi-component system. You have the component, for example, 1 to 5, and you also have the tables to determine your ZI or your composition of the feed, the composition of the distillate, and the bottom product that we quietly assume from the shortcut method. And then if we assume the temperature of the distillate and the bottom and also the feed, of course, you can also get the value, K value at certain temperature and pressure. Okay, I think I have to go back. Okay, so the first one, let's have a look about enriching fraction. In enriching fraction, the calculation will start from the top tray, if you consider this one as the top tray, and then from the liquid from the reflux, because we know the composition of the liquid from the reflux. We know the distillate. So if we consider, let's say it is a total condenser, if you know the distillate and you know the reflux ratio, you can also get the L over here, and also you can get the composition of your liquid. So you know the composition of your liquid, you denote with Xi0 here, and then we can get the Y that comes up from stages 1 using over here, just tray 1 here using the operating line. So we should know for the operating line. And after that, once you know the vapor fraction from the tray 1, you can obtain the liquid fraction that comes out from tray 1 using equilibrium correlation. And then with this one, we can check if it is a feed tray by checking the composition. If the composition is in the feed tray as well. Okay, so in the top column configuration, we have two types of condensation or two types of condenser. The first one is the total condenser, where we assume that all of the vapor here is condensed into the liquid form. So that means the value of Yin in the or I1, it would be equal to the X0 over here. So the stages will start in the first tray. On the other hand, for the partial condensation, you assume that there would be one stage of equilibrium in the condenser because all of the vapors that comes out from the tray number one or the highest tray is actually goes into the condenser to be cooled partially, and you will have one equilibrium stage, and then you end up with product in the vapor phase, which is this is the YID, and you also have the XI1 over here. So your first tray, your first equilibrium stage would be on your condenser, and then your second tray would be, the second equilibrium would be on your first tray. Okay, so what is the equation? So let's have a look. The equation is similar, of course, to the binary compound, but then you will see that we denote it for the, this one is for the operating line. For the operating line, you end up with YIN. So this is the YI, and then I can be the denote I would be the compound. So if you have 5 compound, then you will find I1 to 5. If you have 7 compounds, then you will find I1 to 7. So YIN, the mole fraction of component I at n, or try n, equal to R over R plus 1, a similar equation, multiply with xi at n minus 1 plus xid plus R plus 1. So this is the operating line, the equation that you need for operating line. You know the xid from the composition of the distillate. So you know also this one, so you can get the, the YI1, so you can get this one. Okay, so you know also the XI0 over here, this one, so then you can get your vapor. Okay, for the equilibrium, for the second one, this is for the equilibrium. You have Xi equal to, this is Yi over alpha I over the sum of n to 1 until all the number of components, the total of Yi over alpha I. Remember, alpha I is the K value of I divided by the K of the heavy key component, and or equal to this one yi over xi divided by yhk over x hk. Okay, so this will need the temperature at that tray. So let's just assume that the temperature at the tray would be assumed linear changes at every tray. Let's say, for example, you have your distillate is 50 degrees Celsius, your bottom is 50 degrees Celsius, and you have 10 tray. So you in every stages you added, you can assume that it will increase every 10 degrees Celsius. Okay, So here you calculated the operating line using equation number 1, so you get yi1, and then after that you calculate the equilibrium composition using equation number 2, so you get xi1, and then again checking your operating line to get yi2. So the checking criteria would be lies on this calculation, where xlk over xhk of the feed would be equal to this equation, that LKF minus XLKD multiplied with 1 over Q divided by 1 plus R plus 1 divided by VHK feed minus VHK distillate multiplied with 1 minus Q over R plus 1. So you know all this value, you should know all this value. And then you also know the V in the light key and also in the distillate. So you know the value, the checking criteria. If your tray has this calculation, that means your enriching is stopped. So you have to stop it there. Let's say after you do some iteration until 7 iteration, and then in different stages you did it, and then you got the XLK over HAK in the feed is the same or less than, then that means that's gonna be your feed tray. Okay, it's also the same with the stripping section. You're gonna start from the back, from the bottom there, from the bottom product. You start with the operating line, with this is the equation, and then you also start with the vapor phase. So you know the vapor phase, and also you know the the liquid phase, and you know the vapor phase. So this is your calculation for equilibrium by when you get the criteria again, and then you should stop. Okay, so that is how you calculate the exact method in order to find which stages you are, and then how many stages you need in the enriching diagram, in the etching section, or in the stripping section. Okay, I hope by learning from this video, you also are able to apply your calculation, try it for your multi-component solution, and then you can get the exact method and the stages for the equilibrium, of course, with the temperature in these stages, and also with the composition of each tray. Okay, thank you for listening, and I'm gonna see you in the next session.